First thing we do is we define power functions and exponential functions. We define them algebraically and we define them geometrically. The algebraic definition of a power function of the most basic power function is y equals f of x equals x to the p. The algebraic definition of the exponential function is y equals f of x equals b to the x. This definition, each definition is equivalent to a geometric property of the graph. For a power function, the geometric property is the fact that the function has a constant y factor. Now, I'm addressing this to people who've been through the course. I'm not defining it at this point, so this is just a quick overview. Okay, and exponential function has a property that you have a constant doubling displacement, which we know we have denoted by delta x sub d. Now, there's another way to express the algebraic property, and I'll do that in a minute, but let's see what the geometric property tells us. If you have a constant y factor, then this means that y changes by a constant factor every time x doubles. So here we have value of x, here we have a doubling value of x, double that, double that. Now we do this with compass and straight edge, but I'm just going to slop it down here. So I pick any value for my initial value of y. Okay, so let's say that my y factor is 3/2, then every time x doubles, y has to change by factor 3/2. So if this changes by factor 3/2, that means I've got to have a point that's 3/2 as high as this one associated with this x value. That might put my y value here. Then when I get out to here, y has to be 3/2 times as great. So I construct that, and this is very familiar to us. We do this with compass and straight edge. Everybody should understand how this is done. So I'm just kind of approximating it, and now I get a graph that looks like this. Now, different values of the y factor could give you graphs that look like, let's say, covered up my chalk with a, can give you graphs that look like this, or even like this. And we've explored those. Everybody's constructed those graphs, so everybody should be completely familiar with what this means. Now, the one thing that people might need to think about again is the fact that a constant y factor is equivalent to saying that f of 2x divided by f of x is equal to your y factor. Because, of course, f of 2x, if this is x, f of 2x is out here. F of x is up here, f of 2x is up here. So f of 2x divided by f of x, for this graph where we had a y factor of 3/2, well, this should be 3/2 of this. If I divide this by this, I should get 3/2. So we have this relationship, which we should not only remember, but completely understand in terms of what it's telling us about this power function. So, also, the y factor and the power p imply one another by a very simple relationship. Okay? The 2 to the y factor sorry, 2 to the p equals y factor. So that p equals the log of the y factor over the log of 2. Now this is solved using a relationship that I've given you. You can just use it. And everybody should know that that relationship is a to the b equals c is equivalent to saying that b equals log c over log a. Some people might know the laws of exponents to where they, or laws of logarithms to where they understand this. Other people can just use it. Now, exponential functions, and I've drawn a y-axis here, and I don't need to. We don't need the y-axis, although we will in certain way. We have a constant doubling displacement represented by this arrow. So this is delta x sub d. So if we take a point anywhere at the end or beginning of one of these arrows, like a point here, if we move over through the doubling displacement, x is changed by x sub d so that the value of the function has doubled. And then if we move over that far again, that value will double in turn. We have a point way up here, which means that if we move backwards, the value is halved. And again, this is something we're very familiar with. And then we can slap a y-axis down any place we wish. And if this is a function y equals x to the b, f of x equals x to the b, then wherever we put the y-axis, the point where the curve intersects the y-axis is the point 0, 1. And then there are properties of the exponential function that we develop. Okay? Now, base b is related to the doubling factor delta x sub d, in that b equals 2 to the 1 over delta x sub d. Now, we developed this relationship, and we understand hopefully where it came from. So right there is a synopsis of the most basic things that we know about these two functions.